1 minus ps squared. And if it was a ps1 and a ps2, you'd multiply them together. So therefore, you can check this relationship over here to see which one gives you the best value, which one gives you the greatest probability of survival. So your homework is to build a model that solves this that looks at this problem. And let's go and open your homework assignment. I'm not sure if I've got your homework here, so let me just get it from over here. So this is homework assignment 10. Okay. So in homework assignment 10, in answering the following question, please create a document, which you've done before, PDF, MS Word, that contains heading with your name, date, etc., etc. And you're going to build an over model. You may use elements copied from other models, but each model must be original creation in its totality and attached to this assignment when handed in. Now, I'm not sure what to do about this, because there's a component to this model that you haven't learned how to do that's very easy to do, that I can show you how to do. But in the end, if you don't have a working model, then you can use the model that I provide without any penalty. But I want you to try and get your own working model. So I'll talk about the model that a little bit later. We'll come back to that. So in this work set, you'll undertake a quick and dirty analysis on the viability of a reintroduced population of greater bilbies. Has anybody heard of an animal called a bilby? Okay, I hadn't heard of it until I was looking for a good animal for this assignment. But a bilby is Australia's equivalent of a bunny rabbit. So there's a bilby. So as you know, in Australia, they don't have mammals. Or they did introduce rabbits, then they got out of control, and so they had to introduce a virus to control them. But this is a marsupial rabbit, and there's another one, and as I said, I don't know, who finds it cute? Okay, good. Some of you don't look like you think it's cute. But there is such a thing as a bilby, and it is threatened. And here's a really cute one of a bilby. Big ears. Okay. So there's a bilby, and we're going to try and save the bilby. And initially we have in this one area 60 females, 20 immatures, 20 sub-adults, and 20 adults. And then the data are on the table below. And the question is, you can either set up 60 females in one reserve of 2,000 hectares, or split them in 30-30 in proportion to age structure, and in two reserves of 1,000 hectares each. And you're given the following information. So the bilby is a nocturnal, semi-fossorial, so that means it constructs steep burrows for shelter, omnivore, feeding on seeds, bulbs, and insects, or invertebrates, worms, stuff like that. It lives in Australia, and this is its life table. So if you look at that life table, what is one-time unit going to be from this life table? Yeah, so one-time unit is going to be 3 months. Okay. So now I see I've screwed up this assignment because I said years, 100 years, when I mean 100 time units. So I'm going to have to fix that up. But so at the end of 25 years, that would be 100 time units. So, and we say that the population goes pseudo-extinct if it reaches a value of 8. So if we get down to 8 of them, we're going to take 8 females, we're going to take them out, and we're going to put them in a breeding program. So the program as a whole will be regarded as a success if at least one reserve of whatever size has a viable population that is 9 or more females at the end of 100 time periods. So as I said, I'll fix that and I'll repost it. Thus, in the case of split reserves, you need to take into account that if the population goes pseudo-extinct in one reserve, but not in the other, the population is still regarded as viable. So how to proceed? Use an integer Leslie matrix model like the one that we set up in class. Here, the density-dependent function depends both on n and it depends on a. So in other words, f of n, a, is 1 over 1 plus 10 times n divided by a to the power of 4. So if you're in a big reserve, you put 2,000 in there, and if you're in a small reserve, you put 1,000. And then you run it, starting from 30 and a equal to 1,000 for the small reserve, and you get PS. And remember, PS is applied twice. Or you do it for 2,000, and you start from 60, and you do it in the big reserve. And then you compare your answers, and you say, is it best to put it in one big reserve or 2 small reserves? That's what you're going to calculate. Okay. So here's the model. So this model is just an age-structured model. Now here's M. M in this case is 3. So M in this case I think is, where is it? Let's go back to the work set. Did I close it? Yeah, M in this case is 1. So an individual can either have 1 or 0. And the expected number is that if you're a sub-adult, it's 0.2, and if you're an adult, it's 0.5. Okay? So you can put these values in. So here you've got B2 and you've got B3. B3, for example, is 0.5. Here you've got X0. Remember, X0 is the number of newborns. And the number of newborns is just constructed using this binomial expression. Now, of course, you don't need to put the m's in because the m is 1. But I just made it general so that you can see it generally. But m is 1. dx, that's a proportion surviving. Now, here's where it gets interesting, is that dx1 is equal to... dx1 should be equal to x0, not total pop. Huh. Is that right? So I calculated x1 from x0 and have the proportion survive. Oh, no, I've got that. Yeah. What I said is, So you know about conditional statements. This is a conditional statement. So yeah, dx1 is equal to the binomial of x0 and s0 if the total population is greater than the critical size. However, if the total population is less than or equal to the critical size, then I set dx1 to be 0, which means I've taken them out of the wild. So this is a conditional statement that says if this condition is true, then dx1 equals this expression, otherwise it equals 0. It's the same for dx2. dx2 is equal to this binomial expression, but remember that over here I've multiplied s1 by the factor that accounts for density dependence. So if the total population exceeds the critical size, then this is the number of individuals that will be going from x1 to x2, including the density dependence. Otherwise, they'll be 0 because I removed them. No, that's not the thing. So there's another thing that I'll show you in a minute. And dx3 consists of two expressions, one the x2 surviving and the x3 surviving. So you've got two binomial expressions, and you only apply the expression if the critical size of the population is exceeded. Otherwise, it's 0, and that means the population is now pseudo-extinct. And the extra bit over here, so to calculate whether the population is pseudo-extinct, I have to put in the number of it. So I have a number here, and I say it goes pseudo-extinct. This number should be 8, not 6. Earlier I was working with 6, but this number should be 8. So I'll have to make sure these numbers are correct. So you've got to check them. Time. So these are all lavender because I'm generating a sequence of numbers in each age class, so it's a discrete model. This model over here is an accumulating model. I'm accumulating time. I start out at time equal to 0, and I have a stock variable, and I keep adding 1 to the stock variable. As long as the total population exceeds the critical population, I add 1. Otherwise, I add 0. So what happens is I keep adding to the population time, so I know how many time units I've gone. So as long as it's a critical population, I calculate again and again and again. I've calculated like 37 times, 38 times, 39 times. Oh, it's now equal to or below the threshold. So that means 39 is now recorded as 39 and stays 39 until the end of the simulation. So when I look at the simulation, I say, okay, it says times 39 there, so now I know when the population went extinct. Okay? Yeah? How did I, which one are you asking about now? Yeah, so that's the number 1. And then it's the number 0. So if it's greater than the critical value, I add 1 to it. So that means the time change is equal to 1. What the code is. That is the code. So it says that total time change equals, or total change. And now I can put is, I'm asking the question, so what do I call that? Total, I can't read it up there. I'm having trouble with total pop. So yeah, total pop. So I'm asking, is the total pop greater than the critical number? If it is, then the change is 1. Otherwise, the change is 0. Is that what you're asking? Yeah. So this is the conditional statement in JavaScript. So what it says, that if the change is 1, then because this is a stock equation, this equation sets up the equation time at t plus 1 is equal to time at t plus change. So if time at t is 6, then time at t plus 1 is 7, unless the critical condition, unless the total population has fallen below or equal to the critical condition, then the time of change stays at 6 until the end of the simulation. So when I write out time extinction, then I know at what time the population went extinct. Eric's going to explain all this stuff to you on Monday. Is that right, Eric? Yeah, I saw that in the model that I posted online. I've got n critical here as 6. It should be 8. My n value over here is 2. Oh, huh. Yeah, it should be 1. Right, so that should be 1, yeah. And the other thing that I see that I did incorrectly when I talked about years, but it's 100 time periods, so it's really 25 years. So it's 100 time periods. So you fixed all that. That's great. Okay, I should retire and just have you give my lectures. Yeah. It used to be a project, and I changed it a bit. But because I changed it a bit, I fooled around with the values. Yeah. What I had before is that I didn't have the demography on the birth. I've added that now. Didn't find it very realistic when I didn't. That's why it's a little bit of a mess. And also, I've been having trouble with my eye for about 10 days, so I kind of look at the thing like this. But I'll fix that up and repost the stuff so that I clear up those issues. Okay. So now, are there any questions about the model? Now, there are two things I'm interested in changing in this model. I'm interested in the area that goes into this expression over here, which is, you can see, again, you can't read it at this resolution, but if you have a look at it, it's this expression where I'm dividing, I've got 10 times total pop divided by area. So area is like a carrying capacity. And so as I change the area, I change the carrying capacity in a way. And so I've got that expression in here, and you've got to open the model to have a look at it. But that's the function that sets that. And then the initial value over here that I've set, so it's either 10, 10, and 10, or 20, 20, and 20. So I've got 10 times initial, and initial is either 1 or 2. So I can either set this equal to 1 or 2, depending which case I'm interested in. Okay, so now Now if I run this model, capture load exec, you'll see that it seems to go extinct most of, like this time, it went extinct at time, it's running for 1,000. I actually only wanted to run for 100. So capture load exec, okay. So there, it didn't go extinct. So it doesn't seem to go extinct there. It went extinct once before 100 time period. With these numbers, it doesn't seem to go extinct very often. Oh, wait. So this is in the big one. So I've got 2002. Yeah. Let's see, capture load exec. Yeah. B's. Right, but they should be the, let's see what the values are then. That's 0.5, which is correct. But those are the birth rates. No. Right, okay. Yeah. Yeah, right, yeah. But, okay, let's just see if I make this 0.1, and if I'm, then it'll go extinct much more often if I make this equal to 0.25. So I've got to reset this and clarify everything. So I'm going to do that today and send out the new ones. Okay, so there. Yeah. So now they don't make it at all. They keep going extinct around fairly often. So that doesn't work. Yeah, but that doesn't work very well. So these numbers, the B's were okay because they're females per female. And so it should be, I could make them a bit, so that I could make, I'll make B3 0.5, and then I'll make B2 0.1. That might help a bit. Okay, so there, that went extinct. If you have a look over here at time, where is the extinction time? Yeah, time 58. Okay, and exec, that 55. Okay, that made it all the way through. That made it all the way through. Okay, so these are good numbers. So these are okay numbers. Yeah? The blue line represents time. Time to extinction. So as it goes extinct at time at time 81. No, it's got nothing to do with the blue line. The blue line is just time. I'm just plotting time. If you like, I can take the blue line out. If I take the blue line out, then you'll just see capture load exec. Okay, it didn't go extinct there because it went all the way to the end. It didn't go extinct there, didn't go extinct there, not there. There it goes extinct. Let's execute not extinct. There went extinct. Not extinct. There goes extinct. And so on. Okay, so now if I make this 1,000 and I start off at 1, then it goes extinct very often. Seems to have a lot of, it didn't go extinct there, didn't go extinct there. Goes extinct at least 1 out of 15 times or whatever. So that's reasonable. Okay. So now it's this level that I'm talking about. So what this level does is it enables you to run the model 1,000 times. So here we've got 100, and here we should be running it. Yeah, so here we're running it 1,000 times, and this clock we run 100 times. Is that right? Let's see, capture load exec. Okay. So if you have a look over here now, this tells you that the first run went extinct at time 55, 35. Run 9 made it all the way to 100. Run 18 and 19 made it all the way to 100. Run 23 and 34 made it all the way to 100. Run 70 went extinct at 25, went extinct at 38, and so on. So now I can reset these equal to 2002,